In this lesson we will talk about properties of inscribed angles and then also talk a little bit about secants and tangents. So our first definition, an inscribed angle has a measure equal to 1/2 the intercepted arc. So here's the intercepted arc and our angle measure would be there. So let's say in our example, let's say MP is 92 degrees. So the two letters and the fact that it's an arc stands for the arc MP. So MP is right here, and that's going to be 92 degrees. Then that means the measure of angle MNP is half that. It's going to be 1/2 of 92. So that angle measure here is going to be 46 degrees. So if this is 92, the arc, then the angle inside is going to be 46. That's for the inscribed angle. That means the vertex of that inscribed angle has to touch the side or part of the circle itself, not the central angle. So let's look at a special case. If the inscribed angle is a semicircle, or the arc is a semicircle, well, then this angle in here is going to be 90 degrees. So an angle inscribed in a semicircle is a right angle. Because, remember, all the way around the arc length of a full circle is 360, so halfway is going to be 180, which means the measure of AC is 180. And then what that means is the inscribed angle that cuts across, that intercepts AC, has to be half of 180, so it has to be 90 degrees. It doesn't matter what the lengths of AB and BC are. If it spans the diameter of in a circle, then the measure of angle ABC has to be 90 degrees. Because it's 1/2 of 180, so it's 90 degrees. All right. A corollary to that, two inscribed angles that intercept the same arc are going to be congruent. So if you look at this guy, I'm going to say I have angle ABC or ABD and angle ACD. Well, angle ABC, or ABD, I mean, is here, and he intercepts arc AD, and ACD also intercepts arc AD. So that means they're going to be the same. If they both intercept the same arc, then both of them have the same, both of them are half the measure of AD, which means they are congruent to each other. So angle ABD is 1/2 AD, angle ACD is 1/2 AD, so that means they are congruent to each other. Angle ABD is going to be congruent with angle ACD. Alright, so that was inscribed angles. Now we're going to talk about tangents and secants. So just a definition again. A line in the plane of a circle that intersects the circle in exactly one point, that one is called a tangent. And then here's another theorem. If a line is perpendicular to a radius at its point of intersection, then that line is also tangent. So tangents are always perpendicular to the radius. So it doesn't matter how big the circle or where the tangent sits. If I have a tangent line, I can always draw a radius to it, and it will always be at 90 degrees. So here's that theorem. If a line is tangent to a circle, the line is perpendicular to the radius drawn to the point of tangency. So the tangent is always perpendicular to the radius. And here's another one that you might not think could be true. Tangent segments drawn to a circle from a single external point are going to be congruent to each other. So that, if you look at our diagram here, I have a point P, and from point P I have two tangents coming out, PQ and PR. So PQ, this theorem says that PQ is going to be congruent to PR. And we're going to prove that in class together. So here's a corollary that goes with the last theorem. If two tangents are drawn to a circle from an external point, the line determined by that point in the center of the circle, that line bisects the angle formed by the tangents. So in this diagram we have B as a center, B as a point, and from B we have tangents BC and BA, and also BO going to the center of the circle. We can say that angle ABO has to be congruent to angle CBO. All right, so let's work through this problem. We have a numerical problem here. AB is 20 and OB is 15. So AB is 20 and OB is 15. We want to find AO and then AD. Well, what you have here is, remember, if the line from the radius to the tangent, they're going to be perpendicular to each other. So what I have is a right triangle. Now be careful. A lot of times students won't recognize where the hypotenuse is. Remember, the hypotenuse is always opposite the right angle, so AO is going to be the hypotenuse. Using the Pythagorean theorem, we have c squared is 20 squared plus 15 squared. So that ends up being c squared is 400 plus 225, and that ends up being 625, and this happens to be a Pythagorean triple. C, which is equal to OA, is equal to 25. Now to find AD, we already now know that this is 25 and the radius is 15, so you're just going to add the 25 and the 15. So AD is OA plus OD, so that's going to be 25 plus the other 15, so AD is 40. So don't make these problems complicated. If you're given some lengths and a tangent, look for a right triangle and try to use Pythagorean theorem. Okay, this next example is another one that can be so easy as long as you pay attention. I have a triangle, and it's circumscribed about circle O, and we have some lengths here. I'm going to give you the fact that AF, which is already in the picture, AF is 6 and EB is 7, and we want to find the length of AB. Well, here's what we have to think about. Don't think of this as a triangle. Think of this as a point with tangent lines coming from it. So what we know is that each segment from a point to the point of tangency is going to be congruent. So AF is going to be congruent to AD, which makes AD 6. Same thing down here. BE is going to be congruent to BD, which makes that 7. So the whole length AB is equal to AD plus DB, which means it's 6 plus 7, and AB is 13. That's all you have to do. Don't make it complicated. Finally, one last definition, and then we'll talk more about this one tomorrow. A line that intersects the circle at exactly 2 points, that's called a secant. So that one cuts through the circle. If I have a circle, a secant would look like this. And remember, so that's a secant. And remember, a tangent would look like that. So you need to understand the difference between the secant and the tangent.